Hi there, and welcome to my stack smashing demo. So as we covered in the previous video, there are a few built-in protections that are in most, if not all, modern operating systems. Without these, we can actually perform the exact attack that we're going to do right now, which is a buffer overflow. And with this, we're going to be using 32-bit Linux Ubuntu on VirtualBox. And let's get into it. The first thing we're going to do is we're going to take a look at our vulnerable program, which is cleverly named vuln.cpp. And as you can see, it doesn't really do very much. It simply takes an argument from the command line and it puts it into this buffer here. This is a character string of 100 bytes called buff. And all we're going to do is we're going to copy from the command line whatever is there into buff, and that's it. We don't print anything, we don't do any calculations or anything like that. Just copy what's in the command line, put into this program. That's it. Alright, so what's the big deal? Well, first thing is with this sort of vulnerability, we're able to add what are called shellcodes into our basically override the program's return address and be able to use shellcodes to do all kinds of fun things. And in this example, we're going to spawn a root shell, and we're also going to force the computer to shut down. And this is all achieved using it's assembly language, but they are assembly instructions, machine code, so ones and zeros, but they are written in hex characters. So basically it's a string of hex characters which represents the ones and zeros that would be the actual assembly instructions to perform these things, these actions, that is. So this is our program which we are going to exploit. So the first thing we need to do is we need to bypass these modern safeguards within our operating system. So the first thing that we need to do is disable our memory space randomization. So we're going to do that with the sudo command or sudo command, and we're going to do sysctl, system control, with the W flag to disable the kernel randomization in terms of the memory space. So sudo sysctl-w kernel randomize underscore va underscore space equals 0. It should pop up with a little well, it should ask you for your password, and then it should say kernel randomize space equals 0. And next thing to do is we're going to remove the canary values, and also allow the program to be executable from the stack. And we actually do this, using the G++ compiler. So we're going to do G++ with the G flag -fno -stack protector, stack -protector. And we're going to do a Z flag. We're going to do exec stack of our program, which is vuln.cpp, and we're going to output this to an executable called vuln, and there it is. And now we also want to make sure that we have our permissions set up, so that way we can use GDB compiler to run this. So we're going to go ahead and sudo chown to root our executable called vuln. We're also going to sudo chmod change mode 7755 to vuln. Alright, now that we have our stack smash set up, now we need to do a little trial and error to actually find the end of the buffer. And we can actually do this very easily with the scripting language. We can use Python or Perl. In this example, we're going to be using Perl. And as you can see, I've been using notes here. I don't quite have all this memorized, so I just want to make sure that we're doing this nice and smooth. But just really quick, we're going to do a little demo of Perl in terms of how we use it in the command line. So we're going to go perl-e, which is to execute, and we're going to print, we're going to do like a hello world here, so if I could type. And voila, it says hello world. So we can actually type hello world 100,000 times very, very easily using Perl as well. And as you can see, there it is. That's a lot of hellos. I feel very welcome. And we can actually do the same thing on the command line with our program. So let's try that. Let's use our command line Perl to print the letter A, let's say, which is 1 byte long, if we remember our file type sizes. And we're going to do that, let's try 100 times. After all, that was the size of our buffer, right? So, one thing to also mention, whenever you are using a scripting language in the command line as an input for a program, we want to make sure that we're using a backtick to encapsulate the command. So this is the same key where if I hold shift, I can actually create the tilde. If I don't hold shift, it's what's called a backtick. And this is in fact separate from an apostrophe, which looks like that. So we're going to run our we're going to / our vuln program with the backtick, perl -e apostrophe print double quote A times 100, and then we're going to backtick again, and nothing happens as expected with our program, which doesn't do anything except copy, in this case, 100 A's into our buffer. Well, let's try 110 A's. Let's see if anything different happens. Nope, still the same. Let's try 111. Still the same. What about 112? Oh, it looks like we overwrote our return address, and it was not able to, well, basically we went past the buffer of our program and it ended up crashing the program. So now that we've established where our program crashes, we know that that is the outer limit of the memory space in which this program exists. So what we can do now is we can type a whole bunch of no operation instructions in order to take this buffer, perform a whole bunch of no operations, end it with our shellcode, and then after that we can append the address of this no op slide so that we can basically create this continuous loop for our malicious instructions. So in order to, I guess, find this address, what we need to do is actually go into the program itself and actually look at its memory space. We can actually do this with the GDB compiler, and we're going to go ahead and use gdb vuln to go into our executable. Now, before we actually get started, we need to actually have a shellcode. And as I explained, it is a series of hex characters that represent binary instructions. So this is literally the translation of ones and zeros, but in hex, of assembly instructions to, well, in this case, we're going to use a shellcode to spawn a root shell. And root shell, you can tell you're in because instead of a leading $ as a leading character for your command, it would be an octothorpe or a hash or #, whatever you want to call it. Anyway, so I pulled this from shellstorm.com, and so what we need to do is actually calculate how many bytes this shellcode is. And to do so, we actually look at each one of these /x's. Each one of these /x's is 1 byte. So /xeb, that's 1 byte. /x1f, that's 1 byte. So we want to go byte by byte, count every single one of them, except it gets a little tricky here at the very, very end. So we have this /xff, that's 1 byte. But now we get to non-hex characters. Now these are actual characters. These are 1 byte characters. So this \bin, \s, and h are all individual bytes themselves. So if you count everything and ends up coming out to 45 bytes, you can pause the video and count for yourself. But just remember that this /xff, that's 1 byte, but then this \, 1 byte, 1 byte, 1 byte, 1 byte, up until the end. So altogether it comes out to be 45 bytes. And we've already just established right here that our program crashes at 112 bytes. So if our shellcode is 45 bytes and our program crashes at 112, that means that we need 67 bytes of no operations. Basically, 67 bytes where the computer is reading a bunch of commands that are telling it to do nothing. And the reason we want this is because we want to make our return address as easy as possible to find. So let's go ahead and see if we can find it. So we know, like I said, that this is 45 bytes. So we want 67 bytes of our no-op slide. So to do this, we're going to do a few commands in GDB. The first thing is to set the arguments for our debugger in terms of when it's running our vuln program. So we're going to do the same technique. We're going to go perl -e to execute. We're going to print, and we're going to use a \x90, which is the no-op command. We're going to encapsulate that in double quotes, and we want to do this 67 times. And we want to make sure we add an apostrophe at the end of the execute, the -e. So we want an apostrophe and then another backtick to encapsulate the whole script. So now that that's set, we also want to make sure that we set our breakpoint to the function called main. And it does so. It says our breakpoint 1 is at this memory location in this file on line 7, which is where it was located in our program. So now the next thing to do is run. So now that we are running the program, this is very similar to if you set breakpoints in Visual Studio or Eclipse and you run your program, it'll stop at where you set that breakpoint. So here we are at our main function. So there's a couple things you can do from here. I personally like to just use the command ni, which means next instruction. So now that we've done that, we can see that we are now at this memory location of hex 080484429, and we are at our string copy function where we're copying what's from the command line into the buffer. And what we're going to actually do now is we're going to use GDB to actually take a look at the next 200 bytes. And we do this by typing in x. I think I said previously that this was a this is a backslash, excuse me. I think before I said the other way was the backslash. This is a backslash. 200, so we want to look at the next 200 bytes. And to do that, we want to make sure we put the x at the end. So for bytes, 200 of them, and 200 times. And we're going to do this from the ESP register, which is the stack pointer in a 32-bit system. In 64-bit, it is something different. I do not remember it off the top of my head. But anyways, let's go ahead and enter this. All right, so now we are actually looking at the memory space in our program. So these are blocks of memory right here. And each block has 4 bytes, and within each of these 4 bytes we can actually see the data that is contained. So I'm so sorry. Each one of these are 32-bit blocks. Wow, I went too far. 32 bits. So I'm so sorry. Yeah, each one of these are 1 byte in length. So let's go ahead and see if we see any of our no-ops, which, as we remember, were 90s. So I don't see anything here. So let's type return to look at the next chunk of memory blocks. And it doesn't appear that there are any. Maybe it's in the next one, which should be our 200th. Look at that. We have them right here. So it looks like our no-ops appear starting at this memory address. So this is great. Now what we can do is actually take this memory address, and let's just go ahead and copy it. For our reference, let us have it. Let's just kind of type it in right here, paste. All right. So now that we know where the no-op slide begins, we can, I'll exit this. Excuse me, quit. Yes. All right. So now that we have our memory address for which the no-op begins, now we can actually execute a buffer overflow. So instead of using perl to print 100 A's, well, let's use perl to print not only our no-ops, but also our shellcode, and also the memory address for which the beginning of our no-op will begin. So basically overwriting the return address with this return address, which is our no-op. So eventually what will sort of happen, or what will happen I should say, is that our program is going to run. It's going to go through the buffer. It's going to go into the no-op. It's going to go into the malicious instructions, and I'll call it the maliciousness. And then that is going to go into our new return address. So this is what we're going to be doing. So we want to take our shellcode, which is this guy right here, and let me just get the whole. Let me go Control K just to. Oops, there we go. Just to get the whole thing here. So we're going to use perl to print the no-ops that we need, which, as we established earlier, we need 67 of them. So let's print no-op 67 times. And remember, we want to have our backtick, our -e apostrophe print double quote /x. That's the /, and 67 of our no-ops. Oops, sorry, we do not need this 100. Let's get rid of that. And double quote. And then we want to actually do a comma. So that handles our no-ops. So now let's paste our shellcode here. Let's right-click and paste. Oops, sorry, that's the memory location. Let's try grabbing it one more time here. I wonder if it's going to let me. Alright, I might need to extend this out a little bit here, just to get the whole thing. Nano can be a little cumbersome sometimes. Alright, here we go. Copy. And paste. Oops, oh no, I was afraid that was going to happen. There we go, okay. When all else fails, the up key saves the day. Okay, so that is our shellcode. Now we need to actually include at the very end the return address for which this will apply, or excuse me, for which our program will return. So instead of it returning to the address specified in the compiler and the program, we want to set it to our own. We want to overwrite the return address with our own address. So we are on an Intel system. This is a Little Endian system, and there is a test that you can do, which I won't go over, but I can post the code to see, or for you to be able to test whether or not your system's Little Endian. Basically, all it means is that it reads the lowest bytes first. So, or excuse me, it keeps it stores the lowest bytes in the smallest memory address, or the least significant bit goes in the smallest memory address. Okay, so with that being said, we need to actually insert the memory address as such. So the first thing we want to do is insert the 80, then insert the F3, then the FF, etc. So to do that, we're going to do another double quote. Oh, shoot. Let's make sure our shellcode is also contained within a double quote, like that. Let's go back here and make sure that this is also within a double quote. Perfect. And let's go, oops. All right, now let's make sure that we have our memory address here. So to do that, we want to, let's see here, we want to add /x, and we want to input the bytes of our memory address starting with the smallest byte first. So 80 F3 FF and BF. So again, I'm taking the least significant byte and I'm putting it in first because the computer is going to read this byte. It's going to store this into the least significant bit because it is a Little Endian system. So let's just double check our memory address: 80 F3 F3 FF FF BF BF. Perfect. All right, now let's close that with the double quotes. We have our apostrophe matching from our print here. We have our backtick matching. All right, let's run it and let's see what happens. And it looks like I probably messed something up here. Let's hold on 1 second here. Let's clear so we can get some breathing room. All right, let's see. Where did I go wrong? Print. I made sure. Oh, of course, that's what it was. I did not print our no ops. That is important. Print 90 times 67. That's what it was. So let's do that. Make sure that's times 67. Oops. There we go. 67. There we go. Okay, that looks more appropriate. All right, let's try this again. Hold your breath. What is this? Is that a root shell? Is that a root shell I see? I don't know. Let's see if I can look at something here. Let's see if we can cat the Etsy shadow file here. Shadow. Oops, that's not it. Oops. Sorry, that's not it. It's the, oh gosh, cat. Let's see, did I have the wrong shadow? Ah, there it is. All right, so these are all of our passwords. Fantastic. That is excellent. And we can also, let's see, print our working directory to see where we are. Oh, we're of course in my directory. But yeah, so long story short, we just made a root shell on our system and using a buffer overflow. And this will actually continue as long as the terminal is running. So fantastic. Mission accomplished. And just really quick, we can do the exact same technique and actually find the same thing for shutdown. So that's the end of the root shell. Let's really quickly do the shutdown. I feel like the results would be a lot more satisfying, if you will. So we still have to go through the same process, but I did already sort of pre-write what we needed in terms of our shellcode and in terms of our GDB. So let's just skip the, we already know it's 112 bytes. Let's go ahead and just go into GDB vuln one more time. And we're going to set args. This particular shellcode is 56 bytes long, which oddly enough requires 56 bytes of no op. So we're going to, again, use perl -e to type no ops, which are /x 90, and we're going to do this 56 times. Encapsulate with an apostrophe, encapsulate with a backtick, and oops, I forgot to add the print. Let's do that. All right, perfect. So arguments are set. We want to break main. That just sounds so like death defying or it sounds satisfying. It's break main. It's like I'm breaking the water main. And let's go ahead and run. And we want to, so we're right now inside of the main function. Let's go to the next instruction, ni. And again, we want to look at the bytes. Let me recall the direction of the, oh yes, that's right, x /200. You want to look at the next 200 bytes from the ESP register, ESP. perfect. So again, we're looking for the 9090s. I don't see any here. Next block, type return. Don't see any here. Next block, type return. And I see some right here on the very bottom. Boom. So let's go ahead and use this memory address right here. And let's copy just for our own personal reference here. Oops, messed up my notes. Alright, and let us paste the memory address. Alright, and now let's exit GDB by typing quit. Yes, we want to kill the process. And now let's clear to get some room. And we want to go back to our vuln program, except this time we want to use the 56 no ops. So let's go ahead and I'm just going to copy this script, or this line right here, so that way the last error doesn't happen. So paste, oops, my bad. Let's go back here, and there we go. All right, so I have a second backtick. Okay, so let's comma. That's so we have our no ops established. Let's get our shellcode going, and I'm gonna have to extend out this window. Oh my gosh, it's long. Let's see if I can get the whole thing here. And let's go shift home. No, it's not gonna work for me. Okay. Maybe it'll let me. Nope. All right. Here's what I'm going to do. I'm going to cut this guy. Let's go Control K and let's see if this. Oh wait, this isn't nano. I think what I will do is I'm just gonna have to do this in multiple lines. Sorry, I apologize. I should have had this set up beforehand. And so let's just make this into manageable chunks. And then once we copy it into the command line, it's probably gonna run the program, but then we can just go back and type it up. All right, so whoops, I did each one individually. That's unfortunate. Okay, so I'm actually going to cheat really fast. I'm going to go to my Windows, and I'm going to bring up the code for it from my file, or from my notepad. The beauty about bidirectional clipboard. Copy, perfect. And let's go back into our, all right, here we are. So here's our shellcode. So let's erase all of this and let's paste. Yeah, there we go. All right, now I can go back. There we go, perfect. So now we have our shellcode. Oops, 80. Let's add another comma, and now let's go back and find the. Let's go back and find the memory address that we want to put our return address to. So here it is, and remember this is Little Endian, so we do want to type in the last byte first. So let us add double quotes /x90 /xf3 /xff /xbf, and that should be it. We want to make sure we have our encapsulating apostrophe and our encapsulating backtick, and I just noticed that we have an extra apostrophe right here, which we do not want. And let's just double check everything. So it's going to print double quotes times 56, comma, double quotes, and we have our shellcode ending with double quotes. And just for, yeah, it looks like everything here is good. Notice in this shellcode there's no bin bash, so there is no there's no individual bytes, no extra individual bytes to count. It's all hex. All right, and here we go. Let's hit enter and see what happens. Whoa, look at that. turned off my computer. That's awesome. That is awesome. Well, this has been a demonstration of buffer overflow vulnerabilities. We did a root shell in our system. We also just turned off the computer. Thank you again for joining me, and hope you found this informative. We will see you next time.